In this video, we're going to continue looking at different quality criterion. We're just going to look a little bit more in depth at some of the measures that are going to be new to this section. So the first that we're going to talk about is AIC, followed by BIC, and then leave one out, cross-validation with RMSE. So we're going to look at AIC first, and AIC is represented by this equation here at the bottom. So I'm going to kind of skip down to the bottom for a second. It's going to be minus 2 times the log likelihood function plus 2 times the number of parameters in that particular model. We can also expand that out, and it would be written as n plus n times the log of 2 pi plus n log of r, the residual sum of squares over n, plus 2 times the number of parameters. And I am going to kind of sort of derive where this equation comes from, because you're probably looking at this thinking that this looks like nonsense. Like it just, I'm guessing you're looking at this and you have no idea where this comes from. So I just want to provide enough meaning here, enough background so that it feels like this equation means something, or at least you understand or appreciate that it comes from something. And it's derived from the log likelihood function, which is derived from the normal PDF. And so if you want to think about it this way, remember that when we do linear modeling, we're assuming, whoops, I think I overclicked there, assuming that the distribution of y given x is normally distributed with a mean of beta x and a variance of some value that we'll just call sigma squared. And so beta x, if we're doing multiple regression, is just the vector of betas times the observations that we've observed for each of those predictor variables that we're including in this model. And so if that's the case, then the response variable values that we observe can be modeled as following a normal distribution with that conditional mean and this variance. So we have, I guess I have x here in this equation that I screenshotted from something, when maybe it makes more sense for this to be y, because y is how we usually represent our response variable. And this mu here is going to be that beta x, or I guess we usually write it in the order x beta. Maybe I should be consistent with that. So I'm going to say, I'll say x beta, and over here, I guess to be consistent, I'll call this x beta as well. So then, the likelihood of observing one particular observation for y is going to follow a normal distribution with mean x beta and variance sigma squared, and I can find the likelihood of observing that particular value. Now, if I have a sample of y values, if I have a sample of response variable values, I can represent the likelihood, so the likelihood of y given x beta and sigma squared is going to follow this equation, where I multiply each of these individual likelihoods by one another. So the likelihood of observing this y and this y and this y is going to be the likelihood of this one times this one times this one times this one. So then it's going to be represented by 1 over, again, the square root of 2 pi sigma squared times exp to the minus y minus mu squared over 2 sigma squared. All right, and so this represents the log function, or I'm sorry, not the log, the likelihood function of observing a particular set of data, given that they supposedly have this distribution. Now, you might remember, and if you took Stat 400, hopefully you've learned this before, this is kind of a difficult equation to work with, which is why we often take what's called the log likelihood function. And the log likelihood function is just going to be the log of this equation. And the reason why we do that is because the log has some nice properties where exponents turn into multiplicative values, and multiplicative and division values turn into additive and subtractive elements. So if I take the log likelihood of this equation, what I'm going to get is the log of, and I can actually separate this out, so let me actually do one more step up here. So this is just a constant right here. This is not dependent on my, oops, this should be y sub I. Since this term is not dependent on any of the values that are changing, it is not one of these, but rather this is a constant term, I can actually pull this out and make it 1 over the square root of 2 pi sigma squared to the n times this I equals 1 to n exp to the minus y minus mu sub I squared over 2 sigma squared. All right, so then if I want to take the log of this function, then I'm going to have n times the log of 1 over, and you might remember that a square root is to the half power, and since it's in the denominator, I can actually put this in the numerator and just put a minus in front of it, so it's going to be 2 pi squared, or sorry, 2 pi sigma squared to the negative 1 over 2 power. And then the log of e is just going to cancel out, so then it's just going to be minus the sum of y sub I, oops, over 2 sigma squared. So the log and the e term will cancel each other out. Okay, so we're still not quite to this right here. We still have a little bit of deriving that we can do. The first is that we can further simplify this first term, and we can actually make this minus n over 2. So by taking this negative 1 over 2 term out, we can make it negative n over 2 times the log of 2 pi. And then I can actually pull out the sigma squared term as well and just add it along. So the log of 2 pi sigma squared is just the log of 2 pi plus the log of sigma squared. So then I can also do minus n over 2 times the log of sigma squared. And then this term over here, the sum of y sub I minus mu squared, it's just the residual sum of squares. So I'm actually going to just turn that into RSS. So this is going to be minus RSS over 2 sigma squared. Oops. And now the sigma squared, if I'm finding the maximum likelihood estimate of sigma squared, that's going to be RSS over n. So then I can do a little bit more simplification, and I can make this minus n over 2 log of 2 pi minus n over 2 log of RSS over n. And then this right here, this is going to be RSS over 2 RSS over n. So that's actually just going to simplify to minus n over 2 because the RSS values are going to cancel out in that case. And then I have an n in the denominator of the denominator that just goes to the numerator in that case. And so this would be the log likelihood function of the response variable values that I observe, given that I am predicting their model with x beta as the mean and sigma squared as the variance. So then I get to AIC here, and AIC is going to be some function of the log likelihood function. So basically we're looking at models, and we have different candidates for what beta x and sigma squared might be. And so obviously AIC then is going to favor models with the smaller RSS. So if you think about it over here, the larger this value is right here, the worse the predictive power of this model is going to be. So I'm favoring models that have a lower RSS. They have, in other words, they're a better fitting model. But then there's this other term over here, and that's the 2p, meaning that I'm going to add penalty for having more parameters. So it's not simply which model has the lower residual squared error, it's also which model is using the fewest parameters to do that fairly well. So it ends up balancing those two competing priorities of predictive power with simplicity. Now, all this other part over here actually becomes kind of irrelevant in comparing models. So the reason AIC is the value it is because this has some nice mathematical properties, and there is a way to actually directly compare the AICs of two different models and determine which one is more likely to be the better fitting model. We're not really going to do that in this class, but I just wanted you to kind of know that the reason we have this full clunky equation is because there are nice properties for comparing models and using kind of a likelihood value to determine which model makes more sense and how confident we are of that. But for our purposes, we're just going to be concerned with which model has the lower AIC, which in that case means that we don't really care about this value over here, these constants. We only care about this term and this term, really, for that direct comparison. BIC is very, very similar to AIC. The only difference is literally the penalty term. So if you look right over here, we have, instead of 2p for AIC, we have the log of n times p. So that means that BIC is going to add a larger penalty for adding an additional parameter if the log of n is greater than 2, which most of the time it's going to be because n represents the number of observations that we have in our particular model, so the number of complete rows that we're using with the predictors and response that we include in the model. And so the log of n is going to be greater than 2 whenever n is greater than about 8 or 9, which most of the time we have more than 8 or 9 observations, which means that BIC almost always has a larger penalty for adding an additional parameter for that reason. So BIC also carries some nice mathematical properties, but it's just going to be a little bit more selective than AIC, meaning that if we're using AIC and we're using BIC and we're comparing models, BIC tends to be lower for somewhat simpler models. AIC might be a little bit lower for slightly more complex models. So those two different criteria can be used depending on what our purpose might be, and maybe the AIC model that we get chosen is a little bit larger than we like to use. Maybe BIC would be helpful for selecting a slightly simpler model in that case. All right, let's also talk about leave one out cross-validation. So as you might remember, we've done one-fold cross-validation already, where we split our data into training and test data. We fit the model in the training data, and then we go over the test data and try to make our predictions in comparison to the actual observed values and calculate the RMSE to determine our error in doing that. One disadvantage to this one-fold approach is that we lose data for the fitting process, right? So if we only use about 80% for our training data and 20% for our test data, that might be a significant amount of data that we're leaving out that would otherwise help us make a better fitting model. So instead, what we might consider doing is what's called a leave one out cross-validation process. I should also mention that you could do multi-fold cross-validation as well, where you maybe kind of take turns pulling out different percentages of the data, or like maybe you have 80% training and 20% test, and I could do that 5 different times, allowing each 20% sector to be the test data at least one time. That's another option. We're in this class going to just look at leave one out cross-validation as kind of an answer to this problem, and that's because if we leave out a large amount of data, then we might end up with an influential point in that data. It might just not be a good representation of the data if we do that. So leave one out cross-validation kind of takes turns leaving one observation out of the model fitting process. So we fit our data on all but one point, and then we calculate the residual error, or I should say the squared residual for that one observation that we left out. But then we continuously do that, so we end up fitting the model for as many observations that we have, such that we have left each observation out one time and calculated the residual, the squared residual error for that left out observation. And then we can add that up to determine how much total residual error we have, and then take the square root divided by n of that, determine an average squared residual for our model. So we can do this kind of a shorthand way. So instead of actually iteratively doing this, there is an equation that lets us do this in one step, and that is by taking the sum of the residuals divided by 1 minus the hat value for each individual observation, and then we just sum this up, divide by n, and take the square root. So this notation here, e sub bracket I, or I guess it would be, I don't know, these are like absolute value signs. I'm actually not sure how to pronounce this. But this symbol right here represents the an observation for observation I minus the fitted value when we fit a model including all data besides I in the training data there. So we can actually complete this calculation in one step and determine the leave one out cross-validation RMSE value for a particular model. And this can be helpful for comparing different models to see which model seems to be doing the best at predicting new data, even though like technically we are using all of this data, but we're iteratively leaving a data point out to see how well the predictive power works with unfitted data on all of the data that we have. So for that reason, Luke v. RMSE will favor the simpler model and help us kind of avoid overfitting. And this is an example of how we can kind of calculate that. So if you have your model that you have fitted with the parameters that you have chosen, then you can take the residuals of your model divided by 1 minus the hat values, and then take the mean squared and the square root. Here's just kind of an example of how you'd write that code. It's the same thing that's in the book. And sure enough, even though we already saw that the RMSE of the simpler model was a lot higher than that of the complex model, when we find the Luke v. RMSE, we see quite the opposite now, where actually the Luke v. RMSE of the complex model is much, much higher than that of the simpler model, suggesting that it's actually the simpler model that has the stronger predictive power moving forward onto new data. So here's a summary of everything we've talked about in these first two videos. The first is R squared as a descriptive measure, but it's not great for model selection. Adjusted R squared is a little bit better, in which case we're looking for the model with the highest adjusted R squared, but beating random chance is a pretty low bar to get past, so it's still going to favor fairly complex models. Depending on our goals, maybe that's okay. But we should just kind of keep that in mind, that adjusted R squared is going to generally favor pretty complex models for that reason. Cross-validation is a fairly robust option for prediction. The lower the value, the better, if we're doing Luke v. RMSE as our measure there. So it's a good option when prediction is our priority. AIC and BIC are more flexible options where we can penalize for number of parameters included, where BIC is going to be the more selective option than AIC. So BIC is usually a pretty good option if my goal is to have a simpler model. AIC is probably going to be a little bit more complex. And it's kind of hard to compare cross-validation in AIC and BIC because, or at least I should say, it's kind of hard to compare cross-validation to both of these measures because depending on the situation, cross-validation might be choosier than AIC or it may not be. But generally, you can kind of use all three to determine which model seems to be doing the best, which model seems to have the lowest Luke v. RMSE in addition to the lowest AIC or BIC, depending on your purpose there.